One of the most useful shapes is the triangle. It can be the strongest shape for materials in use for structures. The triangle has 3 sides and 3 angles. And these are the main features. Therefore, we classify triangles in general by using these properties. An equilateral triangle, which is similar to what I've drawn here, has all sides and all angles being equal. So all sides are the same measurement. That's what that means. The bar means that each of the line segments are the same measurement. And all angles are the same. Now, because a triangle has all angles equaling 180 degrees, so angle A plus angle B plus angle C equals 180 degrees, and all 3 are the same measurement, then that means each angle must be 60 degrees. 60 plus 60 plus 60 is 180. Now, an isosceles triangle has 2 sides being equal and 2 angles equal. So these two angles are equal and these 2 sides are equal. This third side is going to be something different, as is this third side there, or third angle and third side. So we have 3 angles being equal, 2 angles being equal. The only other possibility we could have is 1 angle being equal, which is the same thing as saying no angles are equal. So for instance, this could be a scalene triangle. Scalene triangle. You see that each side is a different measurement and each angle is different as well. Now, all of these 3 triangles, the equilateral, isosceles, and scalene, these can all be further classified into properties with their angles. And those are going to be either right, obtuse, or acute. So a right triangle has 1 right angle in it. There's, of course, a lot of different possibilities for this, but 1 right angle, and that means the other 2 must add up to 90 degrees. So this is, let's say this is angle A and this is angle B. This is angle C. If angle C, the measure of angle C equals 90 degrees, and that means angle A plus angle B, the measures of these must equal 90 degrees as well, since they all have to equal up to 180. The only way measure of angle A and angle B can be adding up to 90 degrees is if they're both less than 90 degrees. Therefore, they are both acute angles. So a right triangle has 1 right angle and 2 acute angles. Similarly, we can have a obtuse triangle. An obtuse triangle has 1 obtuse angle, so in other words, an angle that's greater than 90 degrees, and 2 smaller angles. The same reasoning for an obtuse triangle is 1 obtuse angle, and the other 2 must be acute. There's only one more possibility that this could possibly have, and that is all 3 angles are acute. So something like this. This would be an acute triangle. 3 acute angles. So we can use right, obtuse, and acute to further classify the equilateral scalene, or equilateral isosceles and scalene. The equilateral triangle is always going to be acute. That's because the angles on the inside are always equal to 60 degrees. So it has to be an acute triangle. Now the isosceles, this one can be either, it can be actually any one of the 3. It could be acute, obtuse, or right. So all those descriptors apply. And the scaling triangle, I feel like scalings are typically obtuse, but they could be acute, of course, and right as well. I can make a right scaling triangle. This right here has no sides that are equal and one right angle, so that this would be a right scaling. So yeah, scaling can have right, obtuse, or acute. Now the right triangle is a very special triangle. It really is just half of a rectangle. Also, you know, you think of it as half of a square. And so like this is a right triangle. If I created the exact same one, it will fit perfectly and make a rectangle. Probably the most famous theorem about right triangles is the Pythagorean theorem. This is named after a Greek mathematician called Pythagoras. So let's look at that. Pythagorean theorem is just a squared plus b squared equals c squared. And the a and b don't matter so much. What does matter is c. C is always called the hypotenuse. So on a right triangle, this is always going to be angle c, and the side opposite is going to be lowercase c. And then a and b can be either one. Typically, triangles are designated as the opposite side is the lowercase letter of the vertex that you know is opposite of it. Like I said, a and b can flip, but c cannot. C is always called the hypotenuse. The other two are just called legs of a triangle. I should just say leg rather than legs. Okay, now let's use this theorem to actually find some things out. Let's say we have a triangle. Since I'm drawing it, I don't really know if it's accurate. We have 15 and 36. Now 15 and 36, these are both legs of the triangle. That's because they are touching the right angle. That means they're legs. That means the thing that we do not know is the hypotenuse c. So we can find that by using Pythagorean theorem and plugging in, I meant to do it in red, plugging in the legs, which are a and b, and solving for c. So I can say a is this one and b is this one, or I could flip them. It doesn't matter which way I do it. 15 squared plus 36 squared equals c squared. That's how we use Pythagorean theorem. Now we just need to figure out what's the square of these. 15 times 15 is 225. And 36 times 36 is 1296. And we add those two up. That gives me 1521 equals c squared. So when we're trying to find the hypotenuse, you just want to actually do the squares of the legs and add them up until you get c squared equals 1521. Now, to get rid of the square, to get c by itself, all we have to do is take the square root. The square root and the square will actually end up canceling and giving you c by itself. That's a little bit of algebra. And so c is the square root of 1521. Now, I'll make a little caveat here that whenever you take a square root of something, you have to add a plus or minus. That's because there's two answers. If I said x squared equals 4, then x can equal either 2 or negative 2. 2 squared, 2 times 2 is 4. Negative 2 squared is negative 2 times negative 2. Negative times a negative is positive, and 2 times 2 is 4. So both of those give us 4. So we would have to consider the plus and minus version of whatever our answer are. That's how we write it in mathematics. There's two answers to this. However, we're dealing with a triangle, and the side lengths are a matter of distance. Distance can never be negative. So we automatically assume it's the positive version of it. That's why I didn't write it down at all. That's just a little like caveat to be mathematically sound. So the square root of 1521 is 39. In other words, 39 times 39 equals 1521. And we know that c equals 39. So that's the measure of the hypotenuse for this triangle. Okay, let's look at another one. This one I'm not sure how to draw it, but I'll draw it kind of similar to the last one. This time we know that b equals 21 and c equals 35. We do not know what one of the legs are. Now, I said b for 21. It doesn't matter. You could say this is a equals 21. That would be b then. Or you could say this is b and this would be a then. It doesn't really matter. What does matter is c equals 35. That one has to be the hypotenuse of the triangle. Hypotenuse is always the opposite side of the right angle. Okay. We can still use Pythagorean theorem. I'm going to say a is the unknown, and that's what we're trying to find. So a squared, since we don't know what it is, I'll write it as a squared, plus b squared equals c squared. So here I know what the hypotenuse is. That's the reason why I've written something there. Now to find a squared, all I have to do is subtract 21 squared to the other side. And that gives me a squared equals 35 squared minus 21 squared. So this is very different than the previous one. In that previous one, we just added them up. So here we added the two legs together. This is different once again because we know the hypotenuse, and so we subtract from the hypotenuse a leg. So here, just to kind of make it a little bit clearer, hopefully, we have a leg equals the hypotenuse. Here we have a leg, hypotenuse. We don't know what this leg is, so we need to do hypotenuse minus the leg. Previously, we did leg squared plus leg squared. Okay. If you just use the Pythagorean theorem, then, and as long as your naming conventions are correct, then you'll have to do the subtraction. There's no other way to solve it. Okay, 35 squared times 35, so this is 12, 25. 21 squared is 441. That gives us a squared equal to 784. Once again, we need to take a square root of this. And then we're only considering the positive case. A is going to equal 28. So my triangle is incorrect. Oops, didn't mean to do that. So I can't fix it. My triangle is incorrect. A equal to 28. I said this shorter side was A, and so it's actually the longer side. So it should look like this. It should look B equals 21 and A equals 28. That's because 28 is longer than 21. Now, one thing you may notice in both of these triangles is we have a leg being 28, 28, 21, and the hypotenuse is 35. The hypotenuse is greater than both of the legs. In the previous one, we have a leg being 15, a leg being 36. The hypotenuse is 39. So once again, the hypotenuse is the longest side. That's going to always be the case. Because the two angles are acute and the angle opposite the hypotenuse is right, this is always going to be the largest angle. The side opposite of the largest angle is always going to be the largest side. That's just properties of triangles. There's also a triangle inequality that proves this as well. But you need to have the hypotenuse being the longest side. If for some reason you do not have it in your problem, then that means you did something wrong. There has to be, the hypotenuse will always be the longest side. The perimeter of a triangle is found the same way as in other polygons. We just add up all the lengths. In this case, the perimeter is going to equal 26 plus 34 plus 39, which would be 34 plus 39, 99 inches. The area of a triangle is 1/2 base times height. And the reason why it's that way is because two triangles will always make up some kind of parallelogram, or if they're right, it'll make a rectangle, sometimes a square, but a parallelogram in general. And so a parallelogram's area of a parallelogram is base times height. The area of a triangle, well, since it's just half of a parallelogram, is 1/2 base times height. Of course, the height measurement is always what's important here. Just like in a parallelogram, what mattered was this height measurement here, not this side. We don't want that side. We want the height as part of our measurement there. The base was always the one of the side lengths. In the triangle, you have to make sure the height measurement, in other words, this 21 here, that's the height. Wherever that touches, this is going to be our base. I could flip this triangle around a little bit. It'd look, I think, something like this on its side. Now, if this was the base, then that means the height measurement would be this distance right here. So the orientation of the triangle matters for what height you're talking about. What's important to note is that the height will always be at a right angle to the base. So that can help you find what you're looking for. Once you know those things, then the area of a triangle is pretty simple to calculate. Plug them into the formula. 1/2 base times height. So we have 1/2 is 0.5 times 39 times 21. That gives us 409.5. Now I should say that right triangles, for instance this one right here, the base and the height are actually both the side measurements. That's because they meet at a right triangle, or sorry, a right angle. So the area for this one, for instance, would be 1/2 the base times the height. So that would be 0.5 times 28 times 21 gives us 294. So right triangles are typically easier to use. If you're given a right triangle that looked like this, and you knew all the side measurements, what I would do to solve the area is I would actually rotate this thing around to where it looks like this, because then the base and the height are right there, rather than trying to find this height, which would take a lot more work, would be tedious and annoying. So you can just rotate it around, and that's much easier to solve the area for. Okay, I've drawn out 4 triangles here, and we're just going to classify them using some of the names that we learned previously. We're going to classify them by their side measurements and how they work as equilateral, isosceles, or scaling. Equilateral has all sides, all angles equal. Isosceles have 2 sides, 2 angles equal, and scaling has nothing equal. And then we're going to further classify it as right, obtuse, or acute. Right triangles have a single right angle with 2 acute angles. Obtuse has a single obtuse angle with 2 acute angles, and acute only has acute angles within it. So this first one up here, 1, 2, 3, and 4. The first one has, well, if we look at it, we have 15 inches on one side, 15 inches on the other side. We also have 30 and 30, which means, and of course the third side there is opposite the 120 degree. So this side right here is going to be larger than 15. It has to be, since 30 degrees goes to 15 inches on both of the sides. 120 degrees will go to some bigger number. because we have two angles equal, right? This angle equals this angle, and this side equals this side. We know it is an isosceles triangle. Further, it has one single obtuse angle. That angle is obtuse. It's greater than 90 degrees. So we would say this is an obtuse isosceles triangle. Okay, number 2. We see 49, 47, and 84 degrees. So all of the angles are less than 90 degrees, so we know that it's going to be acute. Further, since all of the angles are different, all of the side measurements will also be different. Therefore, no angles and no sides are equal, making it scalene. So this is going to be an acute scalene triangle. All right, number 3. We have a right angle, so we know right off the bat it's going to be a right triangle. What about its side lengths? Is it going to be equilateral, isosceles, or scalene? Well, if we know that this angle here is 40, we also know that this angle here is 90 degrees. That's what a right angle is. 180 minus 90 minus 40 equals 50. This is going to be 50 degrees. And we have a 40, a 50, a 90. All of the angles are different. Therefore, all the side lengths will be different, which means this is going to be a scalene triangle. So it's going to be a right scalene triangle. Okay, number 4. All of the side lengths are 2 feet. Since all of the side lengths are the same, that means all of the angles must be the same. Because if you have the same side length, you have to have the same angle. And if all the angles are the same, that means they have to be 60 degrees. There's no other possibility for that. And we have an equilateral triangle. You could say an acute equilateral because all of them are less than 90 degrees. But that is always the case with an equilateral triangle. So equilateral triangle means it's an acute equilateral. It's by default has to be acute. Now, just a really quick extra piece of information here about regular polygons. Regular polygons are polygons that are the nicest ones to work with, and we've already seen a couple of them in the previous 2 videos, or this video and then the previous one. Equilateral triangles are regular polygons. All angles are equal, all side lengths are equal. It's very nice to work with because it's very well known. And so this would be an equilateral triangle would be what's called a regular polygon. A square is also a regular polygon. All angles are equal and all sides are equal. Of course, the equilateral triangle is a 3-sided figure. The the square is a 4-sided figure. A 5-sided figure is going to be a pentagon. I can't draw it very well. I wish I could. These are where all of these angles are going to be the same, and all of these angles are also the same. And then, of course, a hexagon, a regular hexagon, is a 6-sided shape. All the same, all the same. A heptagon is 7-sided. That's going to be harder to draw for me. A octagon is the 8-sided shape. This is a stop sign. That's the same thing. That one's not too hard to draw. I say that and I make a mistake. All of these are the same measurement, and all the angles are the same. And you can keep going on and on and on. But these regular polygons are very nice to work with because all the side lengths are the same, all the angles are the same. You can like cut them up in different ways, and you'll know that these 2 angles are also the same, and things like that. So if ever you're working with a regular polygon, if the word regular is used in it, that means all sides and all 8 angles are equal. So typically we use or we learn area and perimeter and all those things to help us with more complex problems. We use simple things to learn it and more complex things to solve with it. In this case, we're just trying to figure out how much drywall is needed for this wall. We're looking for square feet, so we're looking for the area of this figure. Of course, we're taking out the door, so that's not included, right? This that's not going to be included into the entire thing. And there's actually multiple ways we can do this. What's important to note, though, is that you cut it up into shapes that we do know the area for. For instance, I can cut right along here, and this top part, I could do it in like green, for instance. This is a triangle, and we know everything about the triangle as well. We know this length here is 17 feet. That's because this length here is 17 feet. We also know that this length here is 14 feet, the entirety of this thing, minus the height of that thing. So 14 feet minus 9 feet gives us 5 feet. So we know that triangle pretty well. Now, the other, let me do it in orange here. This, we can do a couple things with this. We can either break it up into 3 rectangles. That's what my first thought is. But there's actually an easier way of doing it. Like, we could break it up into this. So we have that rectangle, and then that small rectangle, and then that rectangle there. However, I think what's easier to do is to look at the entirety of this, including the doorway, and then just subtract the doorway off of the square. That's probably it's simpler because there's less things to solve for. Anyways, let's look at the green. The green is going to be this triangle here with 5 feet, 17 feet, and this side actually doesn't matter because we're trying to find the area. All we're trying to do is find the area of all of these figures and add them together, and that gives us the area of drywall we need to find. The reason why we don't need to know this third side is because this is at a right angle, just like right here in the picture. That's a right angle right there. So this is our height, and this is our base. So the area of this triangle is going to be 1/2 base times height. That gives us 42.5. Now we go to the orange. The orange is just a big rectangle with side length 9 and base 17. 9 feet, 17 feet. The area of this rectangle is just 9 times 17, base times height, right? 9 times 17 is 153. Now all we have to do left is subtract off the doorway. If we subtract the doorway area off of this entirety square, then we will know what's the area of this thing without the doorway in it. So the doorway is just 7 feet by 3 feet, and it's a rectangle. So the area of the doorway equals base times height, which is actually going to be 3 times 7, which is 21. So the entirety of the drywall, the area of, I guess I'll say DW for drywall since I already used D here. Area of the drywall is the triangle, which is 42.5. That's going to be in feet squared, plus the area of the square, of the orange rectangle, which is 157 feet squared, minus the area of the door, because we added that into this orange square when we didn't need it. We're just going to subtract it off at the end. Okay, Adding those up, 42.5 plus 157 minus 21 gives us 178.5 feet squared.